All right. Thanks for coming. And today I'm very excited to have Bret here with us. And Bret Beheim, he's a senior researcher at the Max Planck Institute for Evolutionary Anthropology. And he's previously he also spent some time in New Mexico, working with HBE, human behavioral ecology. And then I'm very excited to have him here also because he graduated from UC Davis. So he was also this branch of Boyd Richardson camp. And so it will be very great for me and Thomas to have him here to back up what we said so that we're not making up things. So he's here today to talk about cultural evolution. And yeah, welcome.
Thank you very much. Thank you for inviting me. It's very exciting to be here and see this very interesting building. Yeah, so as Chimani said, I'm very interested in cultural evolution. I've worked recently on a number of very different projects, and I thought I'd just mention these here as conversation starters throughout my visit. But also, I've got like a thing that I'm doing. So one of the things I recently worked on, most recently, was a mathematical model of the structure of populations related to cultural diversity and how that relates to stabilizing cooperation, coordination. And that was a purely analytical mathematical model. There was no simulation, there was no empirical data at all. I've also worked recently on a paper studying the decline of cousin marriage as an institution in a population, field population that I work with in Bolivia, the Chimani. This is looking longitudinally at empirical decision-making in a marriage market context. I've also worked in a sort of a deep time context on looking at historical trends and the rise of moralizing religions and sort of the debates about how that can be properly measured in world history. And I also did a project together with my student Han Tran on looking at the sort of information content and the potential signaling value of a South Indian art tradition called kolam, which is a very computational project. So this is a large variety of different things, but it kind of falls under this, this common framework of cultural evolution, which we know now to be definitely worthy of its own conference, the Cultural Evolution Society, and is, I would say, growing very rapidly right now. And many of the core theoretical books, these are three of them, focus on ways in which we can apply evolutionary theory from biology, as it's understood, in cultural topics. But I want, as kind of a hook for this talk, to really focus on the word evolution here and think about why we privilege that word when we're talking about these cultural trends, changes in cultural, some kind of trait we're measuring. There's lots of fields that study cultural change. Network science, economics, computer science, sociology, right? And so when cultural evolutionists are working on these topics, often we use this metaphor or explicitly call this evolution. But certainly this isn't the only group of scientists who are studying these topics from maybe a quantitative or a model-based way. So I think it's useful to talk about, is there anything specific about cultural evolution itself as a field, as an approach, which we can identify and separate from other approaches, say like contagion models in network science? What's special or what's unique about cultural evolution? I think this is more of a discussion point. Maybe Thomas has some ideas as well, but I'll give you my current take on it, because of course, yeah, if we're looking at any kind of trends, legalization of marijuana, woo! Studying this over deep time here, many decades, we're seeing this systematic shift. Lots of different researchers have directed their attention at studying these changes and why they're happening. So I'm going to give you two contrasting examples. I think this is the way I currently frame in my head what the cultural evolution approach brings to studying cultural change. So the first example is from Go. I'm going to talk about Go later today in more depth. If you don't know Go, I'll talk about it. It's a big board game, very old. And this specific anecdote was one of the things that first attracted me to this topic. It came from a Go periodical that was published by two UK amateur players who were doing database queries, the database they built, and learning, from that, what they were seeing was very interesting patterns here in the way that moves in this board game rise and fall. And specifically, they related this anecdote related concerning this this very prestigious Go professional called Go Sagan. His name is Go. He plays Go. That's not a coincidence. It's actually the Japanization of his Chinese characters. When he moved to Japan, he chose the reading of it to say Go because he plays Go. And he, later in his life, became something of like a Yoda figure in the community. And he was commenting in the 90s about this particular sequence as the game opens up here, move 1, move 2, move 3, blah, blah, blah. But specifically this choice here at the star point on move 8. He said, I don't like that. It's not a good move. Just to give you another sense of this guy, he's got a movie named after him, the Go Master. So if the Go Master is saying this move is bad, you might expect it to have an impact. And indeed, if you look at the database, this is a visualization showing each row as an individual player. So we're stacking the players here by their first appearance in the database. And then I'm coloring any particular pixel by whether they used this move 8 or not. And so you can see the sort of column here of red as sort of the efflorescence of this strategy in the 90s. And then it sort of vanishes very abruptly. And that is exactly the point where he gave this interview and said, that's a terrible move, don't use it. It seems like he effectively killed the move. People actually changed their behavior based on they attended to the opinions of senior members of their community. And there has been some recent theoretical modeling work that has been directed at why one might want to copy information from older individuals in a community, if there's an age structure, or from prestigious individuals. This is a common theme in cultural evolution. Specifically in situations where payoffs really matter and the environment is relatively stable. You can see a systematic bias towards copying older people. Okay, so that's the first example. Prestigious older individual says that this is a bad move, everybody stops using it. Second situation, totally different. We're switching systems here. We're in Bolivia, looking at the Chimani forage of horticulturalists. They do not play Go. Actually, they might now, they have phones. But for the most part, Chimani daily activities are oriented around food production, fishing, hunting, horticulture, and the population itself is an indigenous group that speaks their own language. Most Chimani are monolingual. They speak their indigenous language. Some are bilingual and they speak Spanish, or they speak another indigenous language from a neighboring group. I've been working with the Chimani for about 10 years through the Chimano Health and Life History Project, which is an ongoing field data collection project run by Hilly Kaplan and Mike Gerben. And specifically, I've been interested in cultural change in this population. So looking at the frequency of bilingualism in this group. We can assess this through direct interviews to see if people do have some use or some competency with Spanish. And this has been going on long enough now for data collection purposes that we can actually measure the overall trend. In the last 15 years or so, there has been a notable increase in the rate of Spanish competency, specifically among men. And this is a project I'm doing with my student, Brianna Miniature. Spanish is also reliably correlated between parents and offspring, Spanish competency. If the parents speak Spanish, it's very likely that their offspring does as well. And we notice, since we have the full pedigree, that at any given age of life, the actual fertility rate, the probability of giving birth in a given year or having a partner who gives birth, is significantly different amongst people who have command of the Spanish language versus those who do not. People who have Spanish reproduce more, especially men. There's this massive gap early in the reproductive career between Spanish speakers and non-Spanish speakers. Likely this is, connected to the fact that Spanish is extremely valuable as an economic commodity, the ability to work in the marketplace. So it's correlated with a number of other factors which lead to higher fertility. I assert that by this process alone, and really nothing else, you would expect these trends to appear, right? That the language itself will become more common over time because literally they're having more children and the children are reliably inheriting that language, right? So this is very different, right, than the example with Go. We have an example where people are changing their behavior very rapidly, and another situation where people don't necessarily have to change their behavior at all. It's just that they have a very strong differential in reproduction or mortality. By the way, there's also a mortality effect with Spanish too. Spanish speakers tend not to die as much. So it's like double, it's a double whammy, right? And so this, I think, is the connection when we're talking about evolution specifically. So we have some cultural trend, we're measuring it over time. It's an n-gram from Google or something, it goes up and it down. But we can actually separate this out on the level of the individual. And I think this is fundamentally what Darwin's contribution is, or sort of evolutionary biology's contribution is to thinking about populational trends, is that it's really an average of individuals, right? We're looking at lifetimes here. These are all representing a single lifetime where something is happening, and papers are being published, or books are being written, games are being played. And if a particular trait exists within a specific cohort of individuals, it might look like this. And that can produce this cultural trend as time progresses. But it can also look like this, something more like a zeitgeist, where there's a particular moment in time where the entire age structure, all the older individuals and the younger individuals, adopt some trait, and then they don't adopt it, and they lose it. And so that would also produce exactly the same trend, right? So separating out these kinds of processes, I think, is the real value added when it comes to using evolutionary models to understand cultural change. And that's because, specifically, they deal with the concept of force. So force is like a reliable category of process that's acting. And in the context of physics, we might talk about forces as like in a free body diagram. A number of different forces are acting on a specific object, and then the sum of those forces results in the overall change, right? But we can decompose the net change or the net movement into a variety of different forces that are pushing or pulling in different directions. You can do the same thing in demography, right? If you're talking about the change in a population size over time, I'm sort of representing this here as this black line going up and down with time. And I mean, sort of just, basic accounting in population says that the population size at time 2 has to be the population size time 1 plus births minus deaths plus the immigration in minus the emigration out, right? I mean, it's just, conservation of soma or something like that, right? And in the context of evolution, we have similar models for understanding averages, studying the change in averages. And so this is another example, sheep. The sheep do not play Go, guarantee that, but they are extremely useful for understanding Go, I think, or understanding cultural topics. Specifically, this paper that was published in 2009 from Osgood and Tuljeperkar, Cluttenbrock, Tim Coulson. This is a very classic paper in the study of phenotypic change. Specifically, they're looking at body weight among this population of sheep. But they're using these sort of evolutionary principles to separate out every single change that's taking place in terms of the things that happen to individuals over their lives. They die, they're born, there's inheritance from parents to offspring, and also sheep leave and they enter the population. And you can take each of those pieces and add them together to get the overall change, which is the delta Z bar in their formulation. So the approach that I'm advocating here is basically doing the same thing on cultural data sets, is to take some overall change, and this is sort of a delta between 2 time points, and we're measuring out the effect of each demographic or learning component in the way that it changes that delta T. And this is the model that we've developed for this. If you combine these 2 terms here, they're basically covariances. And covariances can be combined together. You may recognize this as the price equation. It's just sort of a demographically explicit cultural version of the price equation. I got one head nodding. So, read Richard's book. Yeah, so price equation applications. That's basically this talk. Yeah, the idea here is that when you separate these things out, they're revealing categories of process, which we could call forces, which are acting potentially against each other at the same time, and they're causing the overall trend to appear as we see it. But separating those out and understanding how big they are is extremely useful for sort of telling a story about this. Okay, so I'm going to talk about two examples for the rest of my time. How much time do I have? Yeah, okay, so first example is with my collaborator Oleg Sobchuk. We're looking at a large corpus of English fiction. We have the full texts of these works from the HathiTrust corpus, although they're scrambled up, and the year range here is roughly a century. So here we're kind of starting from this quote from Max Planck that's called the Planck principle in science studies, that science knowledge over time tends not to change because people, and it's very cynical, but people tend not to be convinced of new arguments, but rather there's demographic turnover, and the older people leave, and so their ideas live. Yeah, this is the opponents eventually die. So this has been abbreviated into the expression "science progresses one funeral at a time." So we're asking if something similar might be happening in literary culture, and there's already a paper that's been done on this data set by Ted Underwood, very great paper. That makes the argument that probably what's going on is cohort succession explains the majority of the variance in literary cultural change. And this is a sort of a stylistic representation of the persistence of topics within specific authors over time. So what Oleg and I are doing is we're looking at individual topical trajectories, and we're using an LDA model to identify specific topics. And these are word associations that are consistently clustered together using the Leighton-Dirichlet allocation. We have 200 different topics that we're tracing over time, and we can measure the frequency of that topic at any given year in the corpus. So just to go back to this idea of a visualization here, this is how we're visualizing the actual forces themselves. So we're looking at some cultural trend. We can measure three different effects on cultural data sets: the effect of individuals entering a particular community, the effect of them leaving, and the effect of what we're calling individual change, of people changing their behavior from time point to time point. And the stack of those three colors gives you the overall change. It sort of tells you the direction of the trend, and you can also separate that as individual components through time. So this is sort of a stylistic example. If we applied that to sort of a simulation model, imagine some event happens like the First World War, and this effect has basically a permanent effect on authors who are participants in this. So over the course of their lives, they're continually weaving those themes into their work. This is very much a cohort model. We're talking about a single cohort of authors who enter the pool of authors, and this topic becomes more common, and then as they age out of the pool, that topic becomes less common. So in that situation, if we do the decomposition, this is what the overall trend might look like. And here it's going to be driven, as you may expect, by entrances and exits, not by individual changes. Nobody's really changing their behavior in this kind of a simulation. Contrast that with something else, like maybe the moon landing in 1969. Everybody's talking about space immediately after, right? The whole population is swept up in this big moment. And so here you're seeing the same thing. It's like in Go, right? Where the whole age structure. So here, if you have that big spike and you separate things out, you'd see something very different. The individual change is first driving the process, it's causing it to be positive, and then it's the exact opposite. As people stop talking about some topic, it just dies, right? And that topic is still driven by individual change. That's what a zeitgeist might look like. And if you graph these in a ternary plot, cohort models, zeitgeist models, they're very different in terms of the balance of forces between these three terms. They occupy different locations. So what happens if you look at the real corpus? It looks like this. So for the most part, individual change is not an important force in driving literary change. If we're looking at the 200 topics, there are exceptions to this, but on average, Underwood is correct. I think Underwood and Basie are correct. If we look at specific examples, like look at Westerns, for example, the rise of Westerns in literature, this is very much driven by the entrance effect over the course of the 1800s, late 1800s. People are entering the literary world talking about Westerns. And then It's driven by an exit effect in the early 20th century as those people leave and they're not replaced. New people come in who are not writing about Westerns. And so this is very heavily driven by sort of the Planck principle. But there are exceptions. If we look at something like this particular topic, government, nation, revolution, peace, politics, it's about politics, right? This is a political topic, which becomes much more common in fiction over the early 20th century. And this is heavily driven by individual change, by individual authors changing their behavior. They start talking about politics more. So there are really exceptions here to the Planck principle. Mostly you'd see successive cohorts as accurate descriptions here, not really with Zeitgeist, but there are exceptions. And then there's also this phenomenon we've noticed that the exit effect tends to be weaker than the entrance effect. And I can talk about that in the discussion, if anybody's curious. Okay, yeah, and then also some informed speculation. Maybe it's the case that modern publishing has shifted. We're really looking at late 1800s, early 20th century here, so it could be that things have changed quite a bit. Okay, so let's talk about Go a little bit more. Yeah, Go is a board game which is very old, and there's been a lot of exciting work on it very recently. I have a package for processing Go games. If you are curious in doing this research, you could check out Kaya. And this database here, which you pay a small amount for, and you can get access to basically all the professional games from the last century and from this century. The cool thing, one of the cool things about Go is that if you visualize all the games together, you take this entire corpus, it forms a very regular move tree. So the first move in the game is pretty systematic, one or the other variant. There's only two options really. There's a third kind of, and you can see the sequence of the game sort of plays out along those lines there. There's dynamics as these moves rise and fall over time, and they correlate with win rates. And if we do the decomposition here, we see something that's very different from the Planck principle, which is that individual learning, people switching their behavior, is the dominant mode of cultural change in the system, or strategic change, if you want to call it. It's very different than the situation with literature. Looking at people's behavior, seeing why they're behaving in certain ways, then enters into studying things like social learning biases. So we do see this sinusoidal shape with respect to recent use of a particular strategy, which is consistent with something like conformity. And we can also see that individual players, this is sort of representing the joint posterior random effect of individual players. We can see that some players are sort of disposed towards consistency with their own past play. Other players are much more willing to copy whatever's hot in the community at the moment. And so there's a lot of variation in sort of the allocation of social learning strategies. But all of this is motivated by the fact that switching matters, individual change matters quite a bit in this system. And so that's why the social learning mechanisms become interesting. I also wrote this up in 2014, and so I have this great quote here that's just mentioning that currently we don't have any strong computer opponents. And of course, 2 years later, we had AlphaGo, and then the succession of increasingly strong superhuman variants. I think AlphaGo 0 is the strongest one. Or no, Alpha 0, excuse me, Alpha 0 was the strongest one. Yeah, this is subsequently, since 2016, totally transformed this game. The general sense in the community, if you read books that have come out in Go, talking about the new strategies, is that everything's gone. Like all the strategies before AI have to be revised. You have to learn new stuff, and this is the experience of any professional player. Yeah, there's also been some really interesting academic work that has shown that humans, as measured by AI, seem like they're also getting better at this game since the arrival of AI, because we have the ability to train with desktop computing AI, which are extremely strong. And there's this paper that came out last year by Shin and colleagues that show that we also see a big spike in diversity in play within this game. So post-AlphaGo, people are seemingly experimenting more, they're trying out new strategies, but most interestingly, I think, and going back to the original story about Go Sagan, is that before AlphaGo, there was a consistent decline in diversity in the game. The game was becoming more homogeneous as people were conforming, they were, sort of discarding variation, and the amount of innovation that's taking place in the game seems to have been getting smaller, even as the game is becoming more popular and bigger. So if we look at individual moves in this game, in the tree, we can also map out exactly where the innovations are taking place. This is something I've been working on recently, sort of building off this existing work. And yeah, as you may expect, one of the things red here means that there's more activity along this particular branch recently, post-AlphaGo, than there was before. So there's a lot of innovation taking place along rare paths. Especially in the very opening, the first move here, this rare variant, all the downstream variants have been heavily innovated on as a result of the arrival of AI. Then one kind of curious consequence of this, given that this is a system where social learning seems like it matters so much, is that there's a very strong change taking place in the signals that we use in social learning models. So if prestige or conformity are important in the game of Go, one thing that's very fascinating is that those are becoming heavily associated with performance in a way that they used to not, that was not the case before. So here I'm taking the database and I'm breaking games up into 4 different eras, which sort of a priori I sort of guess to be different social learning environments. So currently, I mean, you can open up a program on your computer and play a professional level, beyond professional level computer program. It's not difficult. But in 2006 to 2016, mostly we're talking about broadband internet. You can play as much Go as you want with other people. Before that, you've got dial-up connectivity with some people, not a lot, but otherwise your games are mostly located with other people in your community. It's a very segmented population. And then before that, before the 90s, before the internet, we're really talking about reading magazines and reading books as the only way to really share strategies other than direct interaction. So as we go back in time, or maybe as we go forwards in time, we get more connectivity, more information is available, especially systematic information, because people are doing database queries. And as a result, we get this increasingly strong correlation between the frequency of a particular move and its association with its performance. How likely is someone going to win with this particular move? To the point now where it's nearly perfect. I mean, you know, it's not perfect, but I mean, an R squared of 0.87, I mean, come on. So if I was doing a social learning model where the absence of knowing how good a move is, I'm going to use prestige, the whole thing kind of breaks down when you actually do know how good a move is, right? If the information is widely available, you can get the computer saying, oh, that's a good move. And I can give you exact probabilities of winning and the frequency of winning. Then the social learning environment itself is also undergoing a dramatic shift. Yeah?
What exactly is being plotted here? Like, what's each blue dot?
So each blue dot is a node in the decision tree. And we're calculating the use of that node, how often the games in the database reach that node in this particular group of period of time. And we're calculating among those games, how many times did that color win of the downstream points in that node. Yeah. Anyway, so my basic take on this is that the decomposition method works as a starting place. We can identify in this system something very different than what we see in the English literature, which is that individual change matters a lot. People are exposed to social information, they are exposed to their own personal information, they're changing their strategies quite a bit. As a result, in the past at least, we have scope for studying Go through the perspective of social learning heuristics. That people are learning from each other, they're trying to figure out what the best move is. They don't actually have direct information about this for the most part, but they do have the ability to use correlations with other things, like how prestigious somebody is, how old they are, and also how popular a particular move is. If you don't know what to play, knowing that a move is very popular was predictive in my 2014 analysis. It seems to be the case, though, this is much more speculative, and I'm trying to do research on this right now when I have time, that things have shifted quite a bit. And so it's possible that this social learning regime is broken down in a post-AI environment. And that's mostly because we have the ability to do much more direct assessments of the quality of particular moves or particular variations. And so it's possible that we're seeing a reduced scope for social learning heuristics themselves. which would be cool if that's something that's the case. Maybe it's not. Anyway, so that's actually my time. But looking further out, the basic theme here is that we can use decomposition as a technique on any particular data set, as long as we have certain requirements. And separating those terms out is, at least in my experience so far, extremely interesting because it tells us whether certain things matter, like immigration or reproduction or parent-offspring transmission bias, or the extent to which people conform to specific dynamics that are taking place in a population. These are things that you can identify as strong or weak using this particular approach. And it's also possible, I am working on this right now with Oleg, to make more sophisticated models that are more in line with the ones that are used in evolutionary demography, where age and group structuring are explicit components of the decomposition. And you can measure the extent to which, for example, a shift in the age structure causes there to be a shift in the averages and traits, even though no individual is actually changing their behavior. It's just the age structure itself. The shift in that age structure could be the cause of something happening. And that's exactly what happens in the shrinking sheep themselves, why they're shrinking. Yeah, anyway, that's the idea. And if there's potential data sets that people know about that might be amenable to this kind of an approach, I would be really excited to talk to you more. And yeah, thanks to my co-authors, and thank you for inviting me.